My name's Elijah Meeks. I'm over at Netflix. That's me on Twitter, and that's my website. And I'm here to talk to you about complex data visualization with D3. And before I get started, I just want to talk about these two talks that led up to this, Aishikal's talk and Ellie's talk. You guys have no idea how lucky you are. Like, when you were getting into D3 2 or 3 years ago, there was that kind of information being presented in that kind of way, introducing you to it, like Aishikal did, and also explaining this process of actually integrating your questions into pursuing data visualization. That's gold. So I just wanted to thank you guys for that lead up. Some bona fides. I'm the author of D3JS in Action. It's a deep dive into D3. It deals with network visualization and geographic information visualization, and most of the layouts that you have in D3, as well as these scales and axes and things like that. I'm also a senior data visualization engineer at Netflix, and we're always hiring, so if you do data visualization with D3 and you're really good at it, let me know. Typically on Twitter, that's how data visualization people let each other know about that. I work in product analytics, which is in data engineering and analytics, which leads me to my next point, which is why people get into data visualization. I used to have a stock slide for this. It used to be a great thing about why people got into data visualization. But nowadays, people get into data visualization for one big reason. Data visualization is really popular right now, and you can make a lot of money if you're good at data visualization. For those in the back who can't see, this is a giant stack of money. It used to be, my more idealistic slide, it used to be people who get into data visualization do that because they see all these amazing examples. They see these amazing examples on d3js.com, and they see these amazing examples on Twitter, and in this, there's an app called Block Explorer, which shows you D3 functions in action in these small examples. There's all sorts of great, small, self-contained, as well as large and ambitious examples of D3 being used to visualize all sorts of information, all sorts of different ways. And yet, once you get into data visualization, once you start to become a professional data visualization engineer, you find yourself producing 4 kinds of charts. Bar charts, line charts, scatter plots, and pie charts. And why is that? Well, that's a good question. I'm going to talk to you today about D3, but any talk about D3, as we know from both of the talks that led up to this, is more about, it's more than D3, right? D3 is data visualization these days. All of the cutting edge work in data visualization is being done with D3. So you have to talk about principles of data visualization when we're talking about D3. D3, as we've heard earlier, it's the 4th most popular repo on GitHub if you count stars. I don't know. I count stars, but maybe, you know, maybe the more coding among you might count other metrics. And yet, what does D3 do? Well, D3 doesn't produce charts, right? You might go into D3 from HiCharts or some charting library, and you might expect there to be, if you wanted to, for instance, make a pie chart, you might naturally assume that the pie chart layout produces for you a pie chart. But D3 doesn't do that. D3 has a pie chart layout that takes a set of data, as we've seen earlier, and what it does is it appends attributes to that data that are amenable to being drawn on screen as a pie chart. So if you sent an array, like we see up in the top left there, of values, and you sent it to a pie chart, it does not come back with a set of a circle cut into slices. Instead, it comes back with an array of objects with helpful things like start angle and end angle. So I'm going to talk about layouts specifically. I'm going to talk all about layouts. I'm not going to deal with scales and axes. D3 is a big library. It has a lot of different functions. But I'm going to focus on layouts, and I'm going to focus on complex data visualization layouts. So in a sense, D3 layouts, if you had a D3 layout that was for making fajitas, right, d3.layout.fajitas, if you sent it your data, in this case maybe some bell peppers and some chicken, it would not come back to you with a plate of fajitas. It would come back to you with cut up bell peppers and cut up chicken that you might then, if you wanted to, make fajitas with, right? So again, to get back to that pie chart thing, you have a layout, layout.py, takes some data, processes that data, puts drawing instructions on that data. And then if you want to, you know, because you're making a pie chart, you might select all the paths in SVG. I'm not going to get into those details like the last 2 speakers did. But you might take all the paths and use that data and use something called a generator, which draws arcs, to create a pie chart. And so to come back to our example, why is it that this is a good process? Why is it that you want to learn such a low-level library? And how is it that we end up moving beyond just making those 4 kinds of charts? And let's remember that now everybody hates pie charts. So it's actually three kinds of charts, right? You have line charts, bar charts, and scatter plots, which in a sense, if we go back to our d3.layout.fajitas, is like cooking with a chef's knife and a cheese grater and a potato peeler. Which is great. You can make a lot of interesting meals with a chef's knife, a cheese grater, and potato peeler. You can make fajitas, right? But there's a lot more utensils. For those of you who cook, you know this. Here's a data visualization of all the utensils you might possibly want to have. Not only that, this is a complex data visualization of all of the utensils. This isn't about showing the numerical precision of each individual data point, each individual utensil, right? It doesn't show you how many things it can cut or process in some kind of way. It doesn't show you how much they cost or how available they are, something that you could measure with numbers. Instead, it shows you their hierarchical relationship. There are things that divide. Things that divide consist of things like knives, and things like knives consist of things like meat knives. So this is a hierarchical data visualization. And that's important to think about all these utensils, because oftentimes your data isn't amenable to being presented in a bar chart or a line chart or a scatter plot. If you have that chef's knife and that cheese grater and that potato peeler, what do you do when you get an egg, right? You could boil the egg, you could slice it up and put it on toast. I actually saw on Google image search, apparently there are recipes that involve putting sliced up egg on toast. But I felt that you could imagine that yourself. And I've seen people do that. In a demo for complex network visualization, I point out that you could take network data, which we'll see in more detail later on, and you could make a series of bar charts out of that network data. You can. You can take raw data that's really amenable to other forms of representation, and you can process it such that it will fit into one of those 3 charts. And then on the right, there's some, there's a force-directed layout that uses more complex methods to represent more complex structures. And so this is what I mean by complex data visualization. Complex data visualization is about representing more than numerical information for precise comparison. Rather, complex data visualization is about representing geographic or topological, meaning connectivity, or hierarchical relationships. So to get back to our egg, like let's say you wanted to make something interesting with that egg, like a macaroon, right? You can't make a macaroon with just a chef's knife and a potato peeler and a cheese grater. And for those of you who think you make a macaroon by walking into the macaroon store and buying a macaroon, you need to whip eggs to get to it. So there are 2 reasons why we don't use complex data visualization. The first reason is you don't know how. And that's a challenge, but that's actually a pretty easy challenge to solve. There are lots of examples on how to use all of these methods all over the place. The second reason, and this is a harder one to solve, is that complex data visualization uses graphical elements in a way that disrupts the reader's ability to understand what's being represented. So there are these principles in the way that you perceive information represented graphically that are at play whether you're using a bar chart or a network diagram. So here's a few of them from an earlier series I did on Gestalt principles and how they relate to data visualization. I'm not going to go through these in detail, but up on the top left is one of my favorites. It uses 3 competing methods to show similarity. So what do I mean by methods to show similarity? Well, you show that things are similar by putting them near each other. That implies that things are similar. You show that things are similar by giving them the same color. When you read something and you see that things are the same color, you assume that they're similar. You also show that things are similar by drawing something around the things that are similar. And in fact, those signals don't compete with each other equally. That enclosure signal is actually beating out the proximity signal, things being close together, and the color signal. You are going to look at this. 99% of you are going to look at this. There's always one somewhere. 99% of you are going to look at this, and you're going to see the things in the left box as being more similar to each other than the red things or the circles that are close to each other. And so what happens with complex data visualization is all of these principles are at play, and oftentimes they're not accounted for by the designer. So you develop a data visualization product, you think it's great, it's interesting, you show it to people, and they're confused. And they're confused because they're human beings. And that's what happens when human beings see signals like this. One of the most challenging things about complex data visualization is you lose access to some of the most simple tools for making data visualization work. You lose access to labels, you lose access to memory, you lose access to comparison. Uli already talked about this earlier. Comparing these charts, very difficult. It's easy to compare two bars on a bar chart. How do you compare two different hierarchical data visualization products? And so what happens is when you don't account for these principles, when you just take an example of some D3 layout, like a circle pack, and you spend a lot of time understanding it because you have to understand it because you're making it. And then you walk into a meeting and you show it, and people don't understand what's going on. It's not because they're stupid. It's because they are seeing what that thing is showing them. They're seeing circles that are close to each other. They're seeing colors that are conflicting with each other. And as a result, they're confused. So I'm going to talk a little bit about how to mitigate that. And I'm going to talk mostly about the various layouts in D3 that are amenable to complex data visualization. This is created, for those of you who don't know, by taking data visualization and putting it into Deep Dream and creating creepy nonsense out of it. So I'm going to talk about first hierarchical data visualization. This is a D3 layout that I built called d3.layout.orbit, which takes nested data and orbits the children around the parents. And this is a good visual metaphor, except that you can't see any of the rings, but presumably you can see that Mercury and Venus are orbiting around a yellow circle that you assume is the sun, but is actually just a yellow circle drawn in the center there. And various other planets orbiting around it in a different ring, not an actual accurate orbital layout. And then you can't tell, but there's little gray moons that are orbiting around those. So hierarchical data visualization is about taking things. Moons orbit around their parent planets. Planets orbit around the sun. That's hierarchical data. And represented in some form or another. Now, animated representations of hierarchical data aren't that easy to process. We're more familiar with representations like this. This is a dendrogram. It's a representation of hierarchical data. The particular hierarchical data that we're dealing with is labor force aged 15 to 24 in each country as calculated by the International Labor Organization. It's been nested so that the value, whatever they're measuring, has been dropped into buckets. So it's picked a low, medium, medium high, and very high, and dropped it into those buckets, and then nested again, dropped into a container for the geographic location. You're not going to be able to tell that because I don't want you to tell that. I want you to focus on the actual layout itself. That's why there's no legend. You should always have a legend for your data visualization, unless you're that 1%. A legend I would recommend, somebody who works with me at Netflix, Susie Liu, she created d3.svg.legend. It takes a D3 scale and it produces a legend. So you really are out of excuses at that point. The other thing that's going on with this data visualization and all the rest of the data visualization that you're going to see is that it's being rendered in what's called a non-photorealistic rendering format. Now, it sounds kind of stupid, right? Non-photorealistic when these aren't photos. They're computer-generated graphics, but that's the technical term for it. The library is called d3.sketchy. People tend to refer to these as sketchy or handy layouts, right? So the fills are these scratchy little fills. The circles are these hand-drawn looking circles. The lines are a little bit ragged. And I did that because I don't want you, again, to focus on the data being represented. I want you to focus on the layouts themselves and understand that these layouts might represent the same data, but with different affordances, these affordances that Ali already referred to. Now, what's interesting about this sketchy layout, there's a great paper on this from 2012, where they did a study of how people read these sketchy signals. And they found out that, first of all, what you might expect, people who see this sketchy rendering treat these more like works in progress. So if you go into a meeting and you present a data visualization product, and it's your standard sort of out-of-the-box filled SVGs and solid colors, then it's more likely that your audience is going to respond to that as a finished product and not give you feedback if that's what you're looking for. Whereas if you walk in and everything's sketchy, they feel more comfortable to tell you, well, that's not a very good way of representing X or Y. So that's useful. That's probably what you'd expect. That's why they use it for wireframing. What they also found out, though, is that readers are capable of telling the sketchiness level of how you're rendering. So the sketchy has a parameter. How sketchy do you want it? Do you want it to look like, you know, I drew it quickly, or do you want it to look like a 3-year-old drew it quickly? And they can actually tell. They can't tell precisely, but they can tell things, a certain level of sketchiness from one shape to another. So it might be useful actually to encode certain data, for instance, uncertainty or statistical significance using a sketchy function. That nested data that we're talking about here that's suitable for representation using these hierarchical layouts in D3 starts out as something over on the left here. So that's Afghanistan, which everybody knows is the country that comes first in a data set. And that's all the data looks like that I take. So I take in an object. It's got entries, whatever the value is that I'm measuring, percent of the labor force in this case that's age 15 to 24. And it's got values for every year that's in that particular data set. I take that data set, and then I use d3.nest, and I nest it not only by geographic region, but also by, like I said earlier, buckets that split up the data set into countries that have a low percent, a medium high, and a high percent. And it looks like something over on the right. Typically, when you do this, you create a node, a fake node at the top called a root node. And you nest everything inside that. You'll see it in examples. There'll be an array called children or an array called values. The name of the array isn't important. The layouts allow you to define the names of the array. And what we see here is we see the root node up at the top, and it has children, and one of its children has children, and one of its children has children. And that child is finally something that comes out of our original data set. And it's nested in a node called, helpfully, 08221C, and that's the color that it's been bucketed in, so that medium green color that it's being bucketed in. And that is nested inside Asia. So there's a root node that's just for heuristic purposes. It has a series of regions. Each region has 4 different buckets, depending on the percentage that you're putting into the as determined by some kind of bucketing system, whether it's quantiling or quantizing or natural breaks. And here's a more graphical representation of it. The root node, Asia, some kind of value that you've transformed that numerical data into categorical data. This is important because these layouts aren't good at representing numerical data. They're not good at representing numerical data, and especially color isn't good at representing numerical data. So these layouts rely on, rather than a bar chart, say, which you can easily measure the data being represented because people are good at measuring length and width. These rely on color. They rely on size. The nodes are often circles or rectangles. And these aren't good ways to encode values, numerical values. That doesn't mean that they're bad layouts. It doesn't mean that it's bad data viz. It just means that it's not suitable for precise representation of numeric values. So mechanisms like bucketing numerical values allow you to better express that kind of data. Oh, and you'll notice here it has an R value, a radius value. That's not created by the tree layout. That was something that I appended to that. The tree layout doesn't do anything to create drawing instructions for your data visualization that has to do with the size of the circles. It's not concerned with the size of the circles. What it does provide you is it provides you with an X and a Y. You put into this d3.layout.tree a size. It's an array of 2 values, a height and a width. And it gives you back, when it's doing its d3.layout.fajitas kind of thing, it gives you back the position of these nodes based on packing the leaf nodes, the bottom nodes, in the most convenient method, and then building up from there these parents. So the question is, what's a layout like this useful for? Well, there's a strong signal coming from these lines, right? Most of the ink on this page, or a lot of the ink on this page, especially in comparison to some other layouts, is about the connectivity between things. It's not about representing the size of these circles. It's not about representing that numerical value. It's about seeing how things nest and comparing then these sort of categorical and supercategorical values. So seeing how certain regions are overrepresented with large shares of the countries in that region being in certain parts of the labor, having young people in certain parts of the labor force. And more than sort of figuring out how best to use d3.layout.tree or any of these layouts, what I want to remind you is that these layouts represent the same data in different ways, and it's not for aesthetic purposes. It's not like you pick the prettiest one. You pick the one that's most suitable to the question that you're exploring. If you're trying to talk about size, if population is an important aspect of the question that you're exploring, this isn't a good layout for it. And another thing, so when a layout generates those attributes, those drawing instructions, it doesn't necessitate a certain way of rendering them. So typically you see these dendrograms with this curvy lines, and that curvy line comes from a generator called d3.svg.diagonal. It draws a curvy line from point A to point B. You could very easily just use a regular SVG line and draw that line from point A to point B and draw your network however you want. You have the cut chicken and the cut peppers. I'm going to keep going back to that metaphor until you guys walk out. And you can do whatever you like with it. And that's the power of D3, is that it doesn't have built-in charts. But what it does have is a visualization kernel that produces data that's amenable to being drawn in a variety of ways. There's another good thing about dendrograms, and that is a dendrogram is a really useful tool for people who argue that nobody can read complex data visualization. So this is a radial layout. It means that if you'll notice, everything has one parent, and it all ends up in this node in the center. For those of you who can't read it, the node in the center is Duke. The nodes connected to it are Duke and Wisconsin, and so on. This is the NCAA tournament. 40 million people used a dendrogram a couple of months ago. So if those people can use a dendrogram, then whomever you're working with can read and use a dendrogram. Some terminology, you've heard me use it. There's a root node, that's the node at the top, right? The node at the top when it's being vertical, the node in the center when you project it radial. This is the same layout. It's just been represented in a radial manner. And there's the leaf nodes. Those are the nodes at the very bottom. So you'll run into that when you're reading about these layouts and starting to use them. The root node does not mean you root for that node. You do not root for Duke. If you can learn anything from this talk, you do not root for Duke. So, oh, I got so caught up on that I lost my place. Hierarchical data layouts, there are a lot of hierarchical data layouts in D3. Another one is circle packing. So circle packing in this case, it takes the exact same data, comes back with drawing instructions again, X and Y coordinates for your circles. It comes back with an R value because it determines the radius of those circles. But in this case, lines don't connect parents to children. Instead, the parents and the children are related to each other using a direct visual metaphor. They exist inside. The children exist inside the parents. And it builds up and up and up. And what you'll notice is, unlike a dendrogram or a tree map like we'll see later, it uses space really inefficiently. Putting circles onto a square or rectangular screen and packing those circles such that the child nodes are inside them is a really bad use of space. But what it does do as a result of that bad use of space is it strengthens that enclosure signal. You see that circle being drawn around the children. You see that circle being drawn around those children, and so on. And that's really powerful. Now, you notice I did a few things about the I did a few things in regard to how I rendered this. There's actually a circle around this. If you look at a circle pack example, there's the root node circle, which surrounds all of those circles. It's useless. What's that doing for me? I don't render it. I also only render color in that secondary child node. And I don't render any color inside it because I know all of those countries that are at the bottom, the leaf nodes are the innermost circles, share the same rating or measurement of the percentage of youth in the workforce. And what this allows me to do is it allows me to signal some other numerical value. So what can I see? I can see population. Now you can see regions that have very populous countries in certain high or low or middle categories. Circles are not very good for representing numerical information. So you can't expect your audience to go and look at these circles and tell you if this circle is bigger than that circle. They won't. They'll be wrong. They'll be off by 20% or 30%. But just because they can't give you a precise comparison doesn't mean that they don't understand a larger and smaller sense. So again, if the goal of your data visualization is precise comparison of numerical values, don't use layouts that have circles. But there are other data points to represent besides that. So again, the layout itself creates drawing instructions for circles, does not create drawing instructions for lines. And again, how you use it depends on what you decide to draw based on that data. If they need to compare, if your audience needs to compare precise numerical measurements, then use a partition layout. You often hear it referred to as an icicle chart or an icicle layout. So partition layout takes the root node and puts it on whatever screen size you want, and then divides the children up, and divides and represents those children as corresponding below the parent nodes. And what you can do in this case, because people are good at measuring length and width, is they can compare regions. They can compare the aggregated population of a region, the aggregated population of certain measurement categories, and the population of the actual countries. Once you get to a certain point, though, it becomes too small, even if it weren't rendered in a sketchy manner. And you can't expect your audience, you can't just sort of brush that off. If, again, the expectation is that they need to know the exact measurement of that country, then it's a bad layout. Now, there's ways you can mitigate that, using interactivity, hover labels. And the nice thing about hierarchical data is you can also provide instantaneous context. So you could hover over one of these and provide a label. You could hover over this and provide the average value of all its children, or cross-compare in that nested category. You do have to leverage more animation. You have to leverage more interaction with complex data visualization. D3.layout.partition is interesting. Before I get bad slides for a washed out monitor, you guys have a TV though. The one on the left was the data visualization I showed in the beginning. It's a sunburst. Ali already referred to this one. That's using the exact same layout except projecting it radially. To the right of that is what's called a flame chart or flame graph. That's another form that's another type of chart that can be built with a partition layout. Same layout, you're just rendering it all differently. So the partition layout, unlike the tree map or the circle pack, which takes a size and gives you back coordinates in those size parameters, the partition layout gives you back coordinates in a 0 to 1 space, which can really bother you if you finally figured out how to use circle packing and then you started to use the partition layout and it wouldn't draw anything well. Or vice versa, if you finally learned how to use the partition layout and you moved on to circle packing. So keep in mind that these layouts might produce coordinates, might append attributes in slightly different ways, especially once you start to get into plugins and outside of Chord D3. So what I did in this case was I took those 0 to 1 coordinate space and I projected it. I projected it so that it was drawing across 1,500 pixels wide and 250 pixels high. My little monitor up here is complaining to me. And I have no idea what it means. But that's all right. I'll muscle through it. So a tree map is another hierarchical data visualization like the circle pack, except it uses rectangles. And you might think, well, it's rectangles. People are really good at measuring rectangles. I make bar charts all the time. People are not very good at measuring the area of rectangles. So bar charts are useful because they are rectilinear, so they fit within spaces on in UIs and on screen better than circles do. You can pass a padding parameter to many of these layouts, and it will provide a little bit of padding so you can see more clearly the nesting, but it uses up a lot of the space. You end up with single nodes packed into odd positions, like the one on the very top left there that's just a flat line. And there are challenges with this. One way to address this is to use that categorized color scheme, and people will associate this sort of light green, medium green, dark green, light greenish brown, tan, whatever color that is. And this will visually cue them that this is one section, and this is another section, and this is another section. That breaks down when you have sections that are only made up of one color category. Again, it takes a size. This one takes sizes. Takes the size array. Provides you with drawing instructions for rectangles. And if I zoom in, the way that you zoom in with hierarchical data sets isn't through some kind of internal function. You actually filter the data array to create a new root node. That new root node might be Asia. And then you call the layout again. The problem with that is that it runs an automated layout algorithm. And so the positions of these rectangles, the positions, their size, their shape, I shouldn't say their size, the area will be the same, or the ratio of the area will be the same, but the shape will be different. And that's confusing to people because people expect when you're showing the same thing that it looks like the same thing. So you can use animation to animate that transition. You can, again, use increased signaling to remind them of what the labels are for these objects. You just have to take that into account. Networks. This is the result of a force-directed network. It's what people typically think of when we see network layouts. You have these circles and lines. The circle is what we refer to as a node. The line is an edge indicating some direct connection between the nodes. What's a network? Well, it could be a network of friends connected by their friendship on Facebook, or God forbid, their actual friendship. You know, it could be a network of companies connected to each other by patent lawsuits. It could be a network of actors and directors connected to each other by Oscar nominations in the same film. These are all examples of networks, and the actor-director Oscar network is a great example out of the New York Times. Lots of things are networks. To go back to the egg thing, the reason I used an egg was because network data, geodata, hierarchical data, this isn't some tiny subset of data that you don't have to deal with because you deal with numbers. And your customers, your analysts, your coworkers say, just show me the numbers. Well, there's more to data than numbers. d3.layout.force is a bit different from these earlier layouts. You pass it a pair of data sets, an array of nodes and an array of links. The nodes represent those objects that are being shown as circles. The links represent the connections between them. It provides you with drawing coordinates for the individual circles. And you extrapolate from those drawing coordinates the drawing instructions for your lines. You can use lots of different methods to draw the lines between nodes. I've used a bunch of them. I just taught a network visualization workshop and showed off 5 or 6. But typically you'll see lines or curvy lines. Some people hate curvy lines, so watch out for that. This is what network data looks like. There's a source and a target, and then there's other information that you might have about them. So this is a network of creditors to debitors, right? You're connecting one country to another by debt. And that's what this network is over here. Helpfully, no legend, sketchily drawn, so you don't get worry about the underlying data. And from that, what D3 force layout, D3.layout.force does, is it calculates the position of those circles based on a physical simulation wherein nodes that are connected to other nodes pull each other together. Nodes push away other nodes. And as a result, it lays out in a representation of the structure of the network. That physical simulation, that animation you see when a force network is laying out, that's what it's doing. It's these simulated physical forces interacting with each other, which means you have to initialize it. It has a tick function, and on every tick, it updates those values. And on every tick, if you so choose, you could decide to select all of your circles and select all of your lines and update how they look. Or you could choose to ignore that and only update the graphical display once the force network is done running. Another way to represent networks, the chord diagram. In this case, the edge are these sweeping arcs, and the node is the arcs on the border. So there are different ways to represent networks depending on what kind of network you have. If you have a network of flows between nodes, and it's a small number of nodes, then a chord diagram is useful. So if you have a small number of nodes, countries that owe each other money, and it's a network of flows, so the amount of money they owe each other, then you could represent it this way. Same network. And what the chord layout takes is the same data. But then when you lay it out, it provides you with these more interesting drawing instructions. It comes back, this is the result of your chord layout, this object up here that has chords, groups, matrix, padding, and so on. I'm only going to look at 2 of those. The chords are just drawing instructions. They're down here. I'm sorry. The nodes, the drawing instructions are these angle parameters we saw at the beginning of this talk for the pie chart. You pass those angle parameters to a d3.svg.arc, and it draws you these nice little angles. The chords are simply references to the 2 nodes that are connected. And those are passed to another helper function, d3.svg.chord, which generates the sweeping lines between them. Now, I'm going to talk a little bit about maps, but not very much. And that's because there is no d3.layout.map. Right? For those of you who know, how many of you have done geospatial information visualization in D3? You should. It's really powerful. It provides a lot of control. But it's an entire subsection of the library. Instead of there being a d3.layout.map that I pass some information to, and boom, it drops a map on the screen, there's the equivalent of a layout, which is a projection. So you pass a certain kind of projection, like a Mercator projection that we're familiar with from web maps, or the armadillo projection that was used to create this map. This is a data-driven map. It's just a sketchy one. You create this projection, and what that projection does is it takes a set of coordinates in latitude and longitude, and it returns to you the position on screen that those coordinates correspond to. That's what a projection does. In fact, all of these layouts are projections. I like to refer to projections because my background, I started out in mapping, so everything looks like a map to me. But you might start out somewhere else and eventually get to maps, and everything might look like a chord diagram to you. Along with projections, there are other helper functions. There's d3.geo.path, which allows you to pass a well-formed GeoJSON object to it, and it returns to you the drawing instructions in SVG to represent that shape of that object on screen. And there's a lot more to it. Maps are complex, hard to deal with. There's a lot of good examples to get started small and then build up to, well, maybe not that. So there's more to D3 layouts. There are more layouts outside of Core D3, like my orbit layout, right? There's a Sankey diagram layout. It's in the plugins. These layouts follow the general structure that you've seen here. They definitely follow the principles at play with these layouts. But you should expect to have that they might have their own little quirks. And when you deal with them, just remember not to simply take the layout example, whatever example you found on blocks, and generate it and transform your data to suit the layout. Rather, think about how the layout is transforming your data and how you might not want to represent it in that sort of standard way. If you're interested in complex data visualization with D3, I am, it turns out, going to teach a 2-day boot camp on it that deals with geospatial information visualization, hierarchical data visualization, and network visualization, as well as custom drawing. So if you really want to just go hog wild, you've got data and you just want to draw things with it, and there is no layout that you have in mind. For 2 days, it's November 7th through 8th, but it's not a beginner course. It's really not a beginner course. We're not going to deal with sort of enter, exit, update. We're not going to deal with D3 scales. We're not going to deal with any of that stuff. We're going to assume that you know that, and when I say we, it's being taught by myself and Zan Armstrong. And you can go to my site and see more information if this link, if you didn't copy it down in time. But it should get you up to speed. It'll be intense, but if you have already built some relatively complex layouts or plan to between now and then it should prove pretty useful for you. And that's everything. So, thanks, guys.